Hi, GRADE10. Hope all is good. So today we're going to talk about lesson 9.1. Basically, we will talk about hybridization of atomic orbital. Let's start basically by what's the meaning of hybridization of atomic orbital, okay? And why we are using this hybridization. So we use hybridization basically to describe the bonding scheme only when the arrangement of electron pairs has been predicted using VSEPR. So basically we need to use the VSEPR model. VSEPR model, what is it? It's the valence shell electron pair repulsion. We have the table already. We explained the two tables, table number 1, table number 2. What is the difference between each of one? The difference, it's basically the lone pair. In the first table, we don't have lone pair. The second table, it will be applicable when we will have lone pair. So hybridization, it's the term applied to the mixing of atom orbital in an atom, and basically we are talking about central atom, of course, not the terminal atom. Okay? So hybrid orbitals are orbitals obtained when two or more non-equivalent orbitals of the same atom combine in preparation for covalent bond formation. We will see it later on. What's the meaning also of hybrid orbital? Hybrid orbital, the meaning already we explained it, but something we should know, and it's very important, that all equal in energy and electron density, okay? And the number of hybridized orbitals is equal to the number of pure atomic orbital that combine. Moving to the next slide. Now we will introduce basically how many types of hybridization we have. Let's start by the sp3 hybridization. Something you should know, and I will mention it for you, okay? sp3 hybridization. Why sp3? As I said before, we will refer to something basically called what? To something called VSEPR. So sp3, it's used for the molecule of AB4. Why? We have 4 as a number, right? 3. And sp1, it will be 4. So immediately using this way, you can know what is the type of hybridization of each molecule. Find VSEPR. After finding the VSEPR, it will be AB4, AB5, whatever. Using this coding, basically, you can know basically what is the type of hybridization you will have. So let's consider, for example, the CH4. To talk about it, we have CH4. CH4, it's methane. So C, it's 6, 1s2, 2s2, 2p2. Okay? So it has basically, that's the S and that's the P orbital. To draw it, 1 up and 1 down concerning 2s and 2p, that's it. Okay? So CH4, it's AB4, it's tetra, basically hedral. What is tetrahedral? So it has 109.5 degrees. Okay, that's the CH4. After hybridization, what it will be? After hybridization, basically, of CH4, it will be 1. It will be here. So basically, it will be 1. And for the P, it will be 1 up, 1 up, 1 up. It will be S1, P3. So for that reason, we can say that methane, it's sp3. Okay? Let's go back to the PowerPoint. Okay, so consider the CH4 molecule focusing only on valence electron. We can represent the orbital diagram by 1 up, 1 down, 1 up, 1 up. Okay, because it's 1s2, 2s2, 2p2. That's the 2s2, 2p2. Okay? Because the carbon atom has 2 unpaired electrons, as you can see, 1 in each of the 2p orbital, it can form only 2 bonds with hydrogen in its ground state. Also, the species CH2 also is known, it's very unstable. So to count or to account for 4C H bond in methane, we can try to promote it, an electron 2s to 2p. So here it will be 1 up, 1 up, 1 up, and 1 up. Now there are 4 unpaired electrons, as you can see in this. 1 from 4 CH bonds. By mixing 2s and 2p, we mix it 3 orbitals, so it will be 1 up, 1 up, 1 up, 1 up, so it will be sp3. We have 1s and 3p orbital. Let's move now to the other, or to see basically how it will be displayed. Formation of sp3 hybrid orbital, as you can see, we have what? Here we have the s, as you can see, represented by a sphere. And we have the 2p represented by 2 lobes, okay? That's the 2s, 2p, because we have 2px, 2py, and 2pz. When we mix 2s with 2p, we will obtain this one, as you can see. We have mixing in the bond and the covalent bond to obtain this figure, basically as tetrahedral, as I mentioned before, because it's tetrahedral AB4, CH4, and we have basically 109.5 as an angle. Let's continue our PowerPoint. We have sp hybridization now. We have the BeCl2. BeCl2, it's AB2, okay? So it's AB2. Why AB2? Because AB2, it's linear and it's 180 degrees, as you can see. It's linear shape. And 180 degrees, it's represented by BE. Cl, Cl, don't forget the dots. It's 180, it's linear. Okay? We know that it's a ground state that does not form covalent bond with Cl because its electrons are paired in the 2s orbital, so we use the hybridization to explain B behavior. Okay? Let's do the example of B. So B, it's BE, basically it's BE, not B. BE, it has 4, so 1s2, 2s2. So we have 1 up, 1 down. Okay? When I want to talk about hybridization, basically, that's the 2s, 2s, and we have the p. 1 up, 1 up. So this one, it will move to another orbital to have the p. So for that reason, we will have 1s and 1p. So it's s1, p1, or it's represented by sp. And something you should know that we have sp orbital filled, but we have also empty 2 orbitals not filled. How it will be the figure of it? The figure of it, it will be like that. We have the s sphere orbital, we have the p2 lobes. After hybridization, we will have this, okay, this figure obtained after the combination between s and p. Moving to the next one, it's sp2 hybridization when we have, for example, bf3. What we will do in the case of bf3? In the case of bf3, we have B, basically it's the boron trifluoride. It's sp2. Why? As I mentioned before, it's sp2 because we have bf3. It's a 3. 2 plus 1 of the s, it will be ab3. Okay? So it will be trigonal planar. It's 120 degrees. So B, it's 5, 1s2, 2s2, 2p1. Okay? The valence electron of it, it's a 3. We have 1 up, 1 down, and we have p 1 up. Okay? So what will happen after hybridization? After hybridization, we will obtain 1 up, and we will obtain 1 up, 1 up. So it's S and P2. Why 2? Because we have 1, 2. S1 because we have 1. Okay? So for that reason, BF3, it's SP2. Moving to the next slide, basically something you should know that it's sp2 orbitals, and don't forget we have an empty 2p orbital. So we promote a 2s electron to an empty 2p orbital. Mixing 2s and 2p orbital generates 3sp2 hybrid orbital. Of course, the formation of sp2 hybrid orbital, it will be like that. We have one s and we have 2p. So basically, s it's a sphere, 2p, px, py. We will represent it by diagonal planar, as I mentioned before, and the angle, it will be 120 degrees of it. So to summarize everything, the hybridization concept, the concept of hybridization is not applied to isolated atoms. That's an important thing, we should know it. It's not applied for isolated atoms. That's the one. Two, it's theoretical model used only to explain covalent bond. Hybridization is the mixing of at least two non-equivalent atom orbital. Therefore, a hybrid orbital is not a pure atomic orbital. Hybrid orbitals and the pure atomic orbitals have different shapes, as we saw it before. The number of hybrid orbitals is equal to the number of pure atomic orbitals that participate in the hybridization process. So something also you should know, that hybridization requires an input of energy. It means, however, the system more, it will be exothermic. It means release energy. Okay. Now we will do the examples in a next video. BEH2, ALI3, BF3, and we have the PBR5. Now, something you should know about the hybridization of sp and d orbitals for elements in period 3 and beyond. We cannot always count for molecular geometry by assuming that s and p orbital hybridized. Okay? To understand the formation of molecule with trigonal, bipyramidal, and octahedral geometry, okay, we must include the d orbital in the concept. Now we will see in the example. SF6 has octahedral geometry arrangement. We will obtain it later on, and you will see it that SF6, it had sp3d2. Basically, to be sure from our answer, we have 6f. Count the s. We have s1, we have p3, we have d2. So 2 plus 3 plus 1, it will be 6. So basically, SF6, it will be sp3d2. That's the lesson 9.1 basically. Now in the next video, we will see the application or some exercises concerning this lesson. Thank you.